This lesson is rather dry, but we are going to learn about roots of theorems. The actual title of this is 6.5 Theorems about roots of polynomial equations. This is theorem number 1, the rational root theorem. Go ahead, pause the video, write that definition down. Okay, so our job here is, given a polynomial equation, we are supposed to find the rational roots of it. And basically, it kind of all goes down to factoring. You know, when we factor, we look at the factors of our a term, like the one here, and then the factors of our constant term here. So we're going to kind of do that as well, even though this isn't a quadratic equation. We're still going to look at it that way. And that's how you list all possible rational roots. So since the leading coefficient here is 1 and the constant term is -3, by the rational root theorem, the only possible rational roots of the equation have the form of, okay, the only factors of -3 are positive and -1 times positive and -3. So that's where this -3, 3, -1, and 1 come from. And our factors of 1 are 1 times 1 or -1 times -1. So I could have rewritten all of these with -1 on the bottom too, but then you'll see that it's just going to end up being these exact same values. So basically, our possible rational roots are -3, +3, -1, and +1. So to test each root, basically what we're doing is we're going to see, using the remainder theorem from 6.3, we're going to plug each of these roots into our equation and see if the remainder would be 0. If the remainder is of 0, remember that means it's a factor that's a solution to it. So let's test them. Okay, so to test -3, I plug -3 in for x in each of those above. -3 cubed plus a -3 squared minus 3 times -3 minus 3 equals -12. So that is not 0. 3 squared plus 3 cubed plus 3 squared minus 3 times 3 minus 3 is 24. So it doesn't equal 0. -1 cubed plus -1 squared minus 3 times -1 minus 3 is 0. So that means 0 is a root here, or sorry, -1 is a root here. 1 cubed plus 1 squared minus 3 times 1 minus 3 is -4. So that is also not 0. So when we test them, we find that -1 is a root. So the only rational root of this equation is -1. Which when you graph it, you probably see that there's a 0 at -1. This is, I know Slagle teaches this next year, but this is also maybe if a graphing calculator gets taken away from you for this part of the quiz. So this is how you can do it. So why don't you guys go through, if you think you can practice this on your own, go ahead and find the rational roots of x cubed minus 4x squared minus 2x plus 8. Why don't you pause the video and try and do that? If not, I'm going to walk you through it here in a second. So if you look, our last term, our constant is 8, so we have to do factors of 8 divided by the factors of our a term, or our leading coefficient, which is 1. So with that, it'd be positive and -8 times positive or -1, and then we also have positive and -4 times positive and -2. And then all of that would be divided by factors of 1, which is just positive or -1. So basically that means our potential rational roots are 8, -8, 1, -1, 4, -4, 2, and -2. And then when we take each of those values and plug them in to this equation for x, the only one that we get 0 is 4. So 4 cubed minus 4 times 4 squared minus 2 times 4 plus 8 equals 0. All the other ones did not. So our only rational root of this equation, of this polynomial equation, is 4. Now, what can we use this for? So this lesson and last lesson totally go hand in hand. So now we can use this maybe instead of having to use your graphing calculator. So now we can find all of the roots of a polynomial equation without having to graph any of it. So if we look here, let's use the rational root theorem and find the roots of 2x cubed minus x squared plus 2x minus 1. So let's first list all of the possible rational roots. Okay, so factors of -1 are positive and -1. Factors of 2 are positive and -2 times positive and -1. So our only rational roots are positive 1/2, -1/2, positive 1, -1. Once we test all of those using our remainder theorem, when we plug them in for x, the only one that has a remainder of 0 is 1/2. So now we know that's our root. Now we can take this cubic polynomial and we can divide it by the root of 1/2 using synthetic division, and then we'll have our quadratic equation. And so from there, we could either use the quadratic formula, or maybe there's another way we can find our answer. So let's see. Okay, so I know I just taught synthetic division today in class, but basically what you do is you take your 0, which is 1/2, then we list our coefficients of our polynomial equation, so 2, -1, 2, -1, and then we go through the synthetic division process. Bring the 2 down. 2 times 1/2 is 1. -1 plus 1 is 0. 0 times 1/2 is 0. 2 plus 1 is 2. 2 times 1/2 is 1. -1 plus 1 is 0, which we know we should get since 1/2 is a root, or a 0. So basically with these numbers, 2, 0, 2, 0, we can write our quadratic equation. This is our remainder column, so here's our constant, here's our linear, here would be our quadratic, since it builds every term. So we have 2x squared, don't have a linear term, and then 2. So 2x squared plus 2 is our new equation. It is a quadratic equation, so from here, yes, you could do opposite, use your quadratic formula. Negative b plus or minus square root of b squared minus 4ac all divided by 2a. And then from there, you could figure out your solutions. Or what I noticed, that I could actually factor a 2 out, and then I would have x squared plus 1, divide everything by 2, and then I would have x squared plus 1 equals 0, and I can solve this by square rooting. So subtract 1, so we have x squared equals -1, square root both sides, so x equals plus or minus the square root of -1, so x equals positive or negative I, because that's what the square root of -1 is. So our solutions, we just found all 3 of our polynomial equation solutions, 1/2 using the rational root theorem, and then I and -I. Which does this fit? Should, because this is a cubic polynomial, therefore there should be 3 roots. There's our 3 roots, the 1 real root, and then our 2 imaginary roots. Now, sometimes this won't happen. Sometimes you'll have all 3 real roots and it's easier. Other times you won't. Here's another example. Let's go ahead. Why don't you try this one as well? Or we'll walk through it together. And again, let's first test all of the potential rational roots here. So we have factors of 10 over factors of 1. So there's all of them, of our potential rational roots. At this point, once we test them all, you will see that 2 is the only one that when we plug it in for x, we get a remainder of 0 using the remainder theorem. So 2 will be our only rational root here. So we need to find what the other 2 roots are. Now the trick here is you might say, well, hold on. If I graph this, you'll see if you graph this, there are actually 3 distinct x-intercepts. So you might say, well, what's wrong with that? I'll show you here in a second. So let's use this 2 in synthetic divide. Okay, using synthetic division here, you should get 1, 0, -5, 0, which means we have the quadratic equation of x squared minus 5 equals 0. And then again, we can solve this by square rooting. So add 5. Square root both sides, so we end up with x equals plus or minus square root of 5. So that is how, that's why there's 3 x-intercepts, because there's 3 real solutions. It's just these 2 are not rational roots, they're irrational roots. So our 3 solutions are positive square root of 5, negative square root of 5, and 2, which again matches our solution here. Why don't you go ahead, pause the video and attempt this third problem, and your solutions for that problem should be -1 and 1 plus I square root of 2 divided by 3, and then 1 minus I square root of 2 divided by 3. If you have questions on that, make sure you ask. Okay, that is what you should have gotten after you use the rational root theorem and then synthetic division to divide everything, or even long division to divide everything, and then use the quadratic formula to solve. Should have gotten that. 1 plus or minus I squared of 2 over 3. All right, perfect. Now, if you did not get that, make sure you ask questions. We'll talk about it in class. Now on to the hard stuff. Now on to the hard stuff. Just kidding, this is actually really easy. The irrational root theorem. It is written there. Go ahead, copy it down, we'll discuss it. Here we go. Polynomial equation with integer coefficients has the roots 1 plus the square root of 3 and negative square root of 11. Find 2 additional roots. Okay, well, the rational or irrational root theorem tells you how. It's the conjugate of each of those zeros, or each of those roots. So your roots are going to be 1 minus the square root of 3, and then a positive square root of 11, because that's 0 minus square root of 11 will be 0 plus square root of 11. So your solutions are listed right there. Those are the additional roots. So you have 4 total roots there. I know you probably need another example of this, but I'm going to pause the video, or I want you to pause the video and attempt the last one and find the 2 additional roots there. So go ahead, pause it now if you haven't done so already. And your roots should be 2 plus the square root of 7 and then negative square root of 5. I know, really. Last one, imaginary root theorem. This is about as difficult as the one before it. If the imaginary number a plus bi is a root of a polynomial equation with real coefficients, then the conjugate a minus bi is also a root. So here, a polynomial equation with integer coefficients has the roots 3 minus I and 2i. Find 2 additional roots. Well, it's the conjugate of each of those. So it's going to be 3 plus I and negative 2i are the 2 additional roots. Go ahead, pause the video, and attempt this last one. Hopefully you've already paused it, because your answer should be negative 3i and then negative 2 minus I, because those are the conjugates. Therefore, those would be your solutions. And that's it. We will have practice problems with this on Monday that we'll work through for 6.5, and then we'll quiz on Wednesday. All right, thank you. Have a nice day.